Right.
Hello, hi everybody. Welcome to today's CPS talk. It's got a sort of a bit of a physics theme, but Abbie also does some kind of chemistry on the side with her drinks. If you can see her drinks cabinet in the background there. She also does some of her own personal research. So yeah, Abbie is a current PhD student at UCL Physics, but she also runs the UCL Women in Physics Society, is it? Or
group society.
Group, yeah. So I think I think she's also going to chat a little bit about that as well. So really looking forward to her physics talk as well. Cool. If you want to take it away, Abbie, thanks.
Yeah, let's do this. Right. Can everyone see the screen? Yeah,
you can see that.
Okay. It says slow connection for some reason, but the subtitles should appear in a minute. We'll just see. We'll see how this goes. So yes, I'm Abbie Charlotte Bray. I'm a PhD student at UCL in the physics department. I am in the AMOP group, which is the atomic molecular optical particle physics, which doesn't include the high energy particle physics. They're their own separate things. So all the like CERN big experiment people are in a separate bit of physics. But we do a lot of quantum in the group as a whole. And my subgroup is ran by Professor Carla Figueira de Morrison Faria, who I just call her Carla, because she's got a very long, lovely name. And I will be doing a talk on the Inbetweeners, and not the British sitcom, unfortunately. It's actually about one of the methods that I use and how one of the special orbits behaves in a very odd way. It behaves in between something. So as we progress, you'll understand why this is so special. And there's a type of principle called Born type methods, and actually we've moved beyond Born type. What we do is non-Born type. So that's what is meant by beyond Born type. So what I'm doing is I'm exploring the quantum interference in strong field laser matter interaction and attosecond imaging. And as we go on further, I will cover all of those keywords and you'll see how all the puzzle pieces fit together. Now, I'm going to show you this little fella. He is going to come back later. He's a little spider. Please don't ask me why he's got 6 legs. He has 6 legs because he's the happiest spider I could find on clip art. All the other ones were a little bit scary, and we don't really want that in a presentation that already contains very scary mathematics. So let's begin. This is me. Like I said, I'm Abbie. I'm Irish-British, and I am a PhD student. I'm now entering my 3rd year, which is terrifying because I haven't got long left before I have to submit something impressive. I am the first in my family with qualifications over the age of 16. So like I'm the first, not only with GCSEs, but I'm the first in my family to go to university, let alone be doing a PhD. I come from an underprivileged background, which I know that we're meant to use the term social and economically diverse background, but in fact, I'd call it working class. I'm a train enthusiast. I absolutely adore trains. This number is actually incorrect. I've visited a few more recently, but since everything's been quiet on the London Underground, I've had some trips out, but I've nearly been to all of the stations on the system. So there's a picture of me actually in an abandoned shelter down in South London, where they were going to extend the Northern Line and they didn't, and then they ended up using it as an air raid shelter. So that was a really interesting, fun day out for me. So where did I start my physics career? Well, I actually applied to university on the day of the deadline. I had no guidance from my school. They basically told me university wasn't for me. And my parents were like, do what you want. We all just love and support you, but we can't actually help you because, like I said, I'm the first in my family with qualifications above the age of 16. So I ended up getting lots of offers, and my first choice was Imperial, But on the day that I got my results, I kind of freaked out because I just thought Imperial wasn't for me. I thought that I would spend too much time working and not actually enjoying life as a student. And where I chose to go was, as my parents aptly call it, the University of the Chicken Shop, which if you go to Mile End, there is loads and loads of wonderful chicken shops. And anyone who's been there will argue the toss over which is the best one. So that's me. I went to Queen Mary University of London and I did an integrated master's, so an MSci. My thesis for my master's project was in 2D conformal field theory. So I actually am trained through my undergrad and my master's in quantum field theory. That's my expertise. So how I came to UCL is actually quite a funny story. I applied to multiple places for my PhD, mostly in quantum field theory type projects. But by chance, someone I interviewed with left my CV on their coffee table. And that's when his wife picked up my CV and was like, she seems interesting, I want to meet her. So I had an interview with Carla. And actually I realized that as much as I love mathematics, I adore the subject. It's so beautiful to use this universal language and obtain an answer, and this answer can explain something. But the problem is with quantum field theory is that it's like doing maths for the sake of doing maths. You're so far removed from what we perceive as reality and actually impacting the lives of others that I thought that even though I enjoy the maths, I'm kind of doing maths for the sake of doing maths. And actually that isn't that much fun. So when Carla said that this can be seen experimentally, I was really interested that my complex maths that I've learned and really loved could actually be seen in experiments. And even though I'm completely theoretical, I don't touch experiments. I mean, I shouldn't touch experiments because I'm very clumsy. I thought it was pretty wonderful that I could actually live in some sort of reality. So I accepted the offer, and then here I am at UCL. Oh, wow, in my living room, but affiliated with UCL, because who's been to campus recently? So this is my physics family. So this is my group as it is currently, as it is today. There's Carla, the lead of the group. There's our, well, I keep describing Cornelia as our new postdoc. She's not. She joined in February, and because my brain still thinks we're in April, I keep referring to her as a new postdoc, but actually Cornelia's been with us for nearly a year. Cornelia specializes in the Atto clock. And then this is my fellow PhD student, Eloise. And Eloise does another branch of strong field physics, which we'll discuss in a minute. So diversity and inclusion work, as well as doing all my wonderful research in physics, I also do a lot of diversity and inclusion work. As mentioned, I'm head of the Women in Physics group. And also I advocate for underprivileged students coming from a diverse social and economic background. So in all, in all kind of discussions, I'm technically classed as an ethnic minority, being Irish. So I suffer with imposter syndrome because I really believe that I'm a huge box ticking exercise. And the only reason that I was employed was because they needed a quota, they needed some sort of hire. But actually, that's not true. Carla reminds me frequently that I'm here because I do a good job. Wow, sometimes I try to. But imposter syndrome is something that impacts my life on a daily basis and will probably impact your lives as you move further in academia, and probably impacting your lives now. And imposter syndrome is something that we need to break the taboo, because talking about mental health and feeling excluded for some kind of made up reason in your head, it's still really like looked down upon as a sign of weakness. So if you guys have got any questions later on about imposter syndrome or anything to do with my diversity and inclusion work, then please fire away, ask me questions. This little snapshot is actually a picture of me talking at the Royal Institute on imposter syndrome. And it was a pretty scary experience to be there where they do the Christmas lectures and me standing there harping on about all sorts. It was probably one of the most nerve-wracking talks I've ever done. So follow me on Twitter. I do all sorts of things. I post about my personal life in a quirky way. I've got a strange sense of humour. Recently, I took over Researchers Code, which I highly recommend. It's a wonderful platform for women in STEM to come together and discuss the life, the trials and tribulations faced in academia and in industry to do in the STEM branches. So it isn't just chemistry or physics, it's all forms of technology, biology, all sorts. It's wonderful. And there I did an entire week. So every day I did a different topic, one including my work, others including life in lockdown, like I said, imposter syndrome, burnout, mental health, autism. There's all sorts on there. So feel free to check that out and you'll learn a little bit more about me. Now, so why am I here? Well, it's because of physics and maybe a little bit of chemistry too, because I do deal with atoms and sometimes molecules, but molecules are scary because there's a lot going on. So I'm not doing anything like proteins or anything crazy like that. I'm purely mostly looking at very simple little happy atoms. And I just wanted to put this photo because this is me at a conference on the fields in Normandy. And this is actually a group of people from all around the world. And they all are in photoelectron holography, which is my field. And it's wonderful that we can collaborate with experimentalists, theorists alike, and create something beautiful. So let's begin the science part. Okay, so my realm of physics is strong field. So it's a field, laser field, and it's strong. Hopefully that makes sense. That's probably the most easiest bit to explain during this talk. And within strong field, there's all sorts of different subsections that research goes into. So with our group, there's photoelectron holography and there's non-sequential double ionization, which we call NSDI because, as you can see, that's quite a mouthful. So with photoelectron holography, that's my branch and the other is Eloise. And here we've got a nice little table charting as time has progressed, which funny enough, this table is a little old now. Where's 2020? Come on. Well, we're all going to forget about this year because it's been terrible. But you can look at the increase of focus intensity of lasers as time has progressed. So, and it's just going to keep progressing. And that's wonderful. And that's thanks to experimentalists and theorists collaborating and working together. So I work in attosecond. So it's a second. It is 10 to the minus 18th of a second. So really, really, really small. And really, really, really small means that we get to look at atoms. And when you go really, 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 really small, that means you enter into the quantum realm. And obviously the quantum realm itself poses new types of interference patterns, new information, new dynamics, and also difficulties in the mathematics, because in the classical world there's very much linear dependence, and then when you go to quantum things change quite a bit. So I'm all the way over here, and as you can see that's incredibly tiny, and even the pico is still tiny, it's much larger because you're looking at molecules in solids. So let's talk about quantum interference quickly. So when we're in the quantum realm, there's more than one possible pathway from A to B. So that means with all these pathways, all these choices, all of these situations you can get, it means that amplitudes will interfere, and that causes beautiful patterns, it causes problems.
Has my screen frozen or has Abbie's?
I think it might be Abbie's because it's frozen for me too.
Oh, okay. Oh, I think she's logged off. She might be trying to get back in. Sorry, everybody. We're just having a bit of technical difficulties. I'm sure Abbie will be back in a tick. Maybe if you want to grab a drink or anything. And I will try and get in touch with her. Oh, I think she's back. Oh,
yeah.
hey. Oh.
Hi. Hang on, let me just, there's context. I don't know what happened. I think that was my Wi-Fi dropping.
No worries. This is a common thing that I think we're finding. So yeah, glad you're back.
Yeah, I'm using my phone now. I'm using my 4G because
cool.
I think that's safer. So where did we get to? Did we get to the quantum interference?
I can't remember what the screen looked like. I think it was the first sort of sciencey slide, I think.
Okay. We will go from...
Yeah, that was that one.
Yeah. Okay.
Cool.
So,
thanks.
That's cool. Okay, let's do this again. So sorry about that, everyone. Oh, and look, I've got captions now. This is even better. So quantum interference is as like, there we go. Hang on, just sorting out something. So when we go to small, we go to the quantum realm or the regime. I sound very much like the Ant-Man movie when I say quantum realm. I do apologize. And so there's more possible paths from A to B, and that actually creates amplitudes that interfere, and that enables us to see some patterns that are not necessarily described with classical mathematics and in the classical realm. And you see these patterns in both experimental and obviously in theoretical approaches. So let's have a look what's next. So this is an outline of what I do. So I do photoelectron holography, and it's a way of imaging a target in such a way that you're able to display its momentum in a diagram like this. And that itself then tells us about the dynamics. So this diagram is called a photoelectron momentum distribution, and you're going to see a lot of them during this talk. This one is actually an experimental one. So this is actually taken from an experiment. So if all of you could just take a snapshot in your brain of what this looks like, you can see there's some fringes, there's some frilly bits, kind of looks like a sunrise. And when I show you in a bit some of mine, you can kind of compare and see how they are comparable. So how photoelectron holography works is it's induced by an interference of two electron trajectories, both driven by the strong laser field. On one of the electron tunnel ionizes and is accelerated by the strong laser field, which dictates its final momentum, which is something we look at. This electron trajectory serves as the reference wave or beam or whatever word you want to use. And alternatively, the electron may scatter off, that's the weird probe wave, and that serves as the signal wave or probe. The holographic interference patterns of two trajectories is observable, such as in this diagram. Now, that's all fine and good if we're doing an experiment. Where do I fit into this world? So there's many, many theoretical models. And one very popular one is the strong field approximation, which we call the SFA. And the SFA is good for a purpose, but it has some overwhelming limitations, which we will come on to later in this talk. I work on the Coulomb quantum orbit strong field approximation, so the CQSFA. So it's based on the SFA, but it's got some additional little awesome bits, which changes the mathematics, but also it changes what we get out of it. So we provide a deeper understanding with this model, and it gives you the ability to probe further interference patterns linked to specific orbits. Don't worry, we're going to get to what an orbit is, and phase differences, and it's more realistic because you know why? It involves the Coulomb potential. Other models don't. The strong field approximation doesn't involve the Coulomb potential. And we know fundamentally that the Coulomb potential is there and is really, really important. So, photoelectron holography and interference patterns. We are looking for the interference patterns. That is what tells us the information about the target. So we're going to work through about how we get to these interference patterns, what do they mean, and how do they help us understand what's going on. So photoelectron holography is for ultra-fast imaging of matter. It allows retrieval of transition amplitudes and phase differences, which, like I said, appears in the patterns. And most particularly and important is it has high resolution. So it makes things nice and clear for us. So interference patterns are obtained through tunneling, as I've mentioned previous when we talked about quantum. And the model that we use is the three-step model. So we start off in the wow. Strong electric field distorts the potential. Tunneling occurs. The electron is accelerated, and then the direction of trajectory is changed if the field is oscillating. Electron arrives back to the same place, but with higher energy. Then it releases a photon. So it's just, you can see from step one, pops out, moves, then there's the recollision and drops back down. So what are these interference patterns and why are they linked to orbits? So we use orbits because orbits provide a physical representation of the three-step model I showed you. Basically, orbit shows us the three-step models. So why is this useful? The interference patterns shows the interactions between these orbits and also indicates the type of scattering, whether we have direct or whether we have rescattered, or maybe we have something in between. So you can see the crux of this talk. So types of scattering. The SFA, what we'll call the basic model, tells us that there's two types of scattering. There's direct, so straight to detector, or there's rescattered, where it can come out, come back to itself, and then to the detector. So how we can tell what regime they live in is by looking at the pondermotive energy. Don't worry, we're going to get to a definition of what pondermotive energy is. If it lies in 2 pondermotive energy, that means it's direct. So when we look at the PMDs, the photoelectron momentum distributions, we're looking at something in this tiny kind of middle bit, because if you imagine this circle is at a 2 UP cutoff, whereas 10 UP is rescattered, and that's much farther out in this kind of ridge. So it's much farther out on the diagrams. So these are very basic PMDs. They don't actually tell us a lot. They don't tell us about any interference that's particularly happening or anything interesting about the dynamics. So as I said, the strong field approximation has its limitations. It uses a Born type approach, which therefore categorizes that something is either direct or rescattered, and it's well defined. It's a binary system. Yes, no. Are you direct? Are you rescattered? You must be one. And the continuum is approximately field-dressed plane waves, which doesn't allow the Coulomb potential and the laser to be on an equal footing because it doesn't involve the Coulomb potential at all. So rescattering tend to be around the polarization axis, and it doesn't show any other. So if there was a case where rescattering wasn't, then it wouldn't show anything at all. And we know that there is a case where polarization is actually around, not around the axis. So therefore, that's where the SFA lets us down. Also, it's not able to probe bound states whose orientations is perpendicular to a field. So I'm going to use an example about my research where we have helium and it's an excited state. So there is an orientation which is parallel to the field and also also an orientation where it's perpendicular. And if you use the SFA, you don't get those results. And I will show you the power of the CQSFA, my model, enables us to do that. So is this reality? Like I said, it isn't. It neglects the Coulomb potential, and that's fundamental in the dynamics of atoms. So how can we fix this? Simple, you chuck it in. But when you chuck it in, well, when you chuck it in, you get a picture of Andy. When you chuck it in, the mathematics gets more complicated. The reason I just put this young gentleman on the screen is that he's recently left our group. He's now in Barcelona at ICFO, and we miss him greatly here at UCL. He and Carla developed the CQSFA extensively over the last few years. And thanks to him, I'm able to understand partially what's going on in this crazy world. And I thought it was wrong not to mention him in this talk. So thank you, Andy, for all the work you've done, all the help you give me. So like I said, when you chuck in the Coulomb potential, things get crazy. The laser field is on an equal footing as the potential. It now becomes a non-Born type approach. So this theory is formed through S-matrix theory, and therefore you can produce scattering amplitudes. Using path integral techniques combined with saddle point approximations, you're able to derive saddle point equations, which in this case gives rise to 4 orbits. And these 4 orbits are the 4 possibilities that the electron may follow per laser cycle. So let's find out a little bit more. So here are 4 orbits done in a little cartoon that I made. And you've got orbit 1, which when you assess it, very much direct. Orbit 2, very much direct. Orbit 4, rescattered. You know, it lives in that 10 UP regime rather than the others that live in that 2 UP bubble. And then orbit 3, even though this diagram looks like it's equal to orbit 2, orbit 3 isn't. Orbit 3 doesn't live in the 10 UP regime, but nor does it live in the 2. It's somewhere in between. See, Inbetweeners. It's a hybrid. And that's something we're going to discuss when we get to my research results. Also within our mathematics, we involve a quantum prefactor. This includes bound state information, which, as we address, the SFA lacks, and it's contained in the prefactor. So improved transition amplitudes and more quantum features, and there's a stability factor for the mathematics involved also. So before I go to my results, I want us to have a little look at some key words that I've mentioned and I'll be talking about more in detail. So, ionization potential, what on earth is that? It is the minimum amount of energy required to remove the most loosely bound electron. So, it is the minimum energy to remove something, in this case, electron. UP, Ponder motive energy, is the cycle averaged energy of a free electron in an electromagnetic field. So this is what we describe as energy. So when I refer to energy, I'm referring to Ponder motive energy, not potential or kinetic or any other types of energy you've ever come across. Here's the equation for it. And I work in AU, atomic units. So therefore that's why the equation is so neat and got not many dependents, because I make basically everything one. So now we need to talk about what tunnel ionization and tunnel exit is. So the electric field component of the laser field distorts the Coulomb potential as mentioned in the 3-step model, and it does it enough where the electron tunnels out. So the point in which it tunnels out is known as the tunnel exit. This can be both defined spatially or in terms of time, so what time did it exit? But today we're going to focus on defined spatially, so at what point in regard to position the exit occurs. So I'm now going to go into my results and my research, particularly with what I do. And there's actually a funny story behind it. So today we're going to be talking about varying IP, so ionization potential. And why did I decide just one day to be like, oh, I'm going to start varying it? Well, I didn't. I was given IP in an email to do an investigation with a collaboration. And they said, the IP that we want you to run in your code is this. So of course I ran it. Then I put the results in the paper and everything, and they were like, oh yeah, that's the wrong, oh, sorry. they're like, oh, that's the wrong IP. And I was like, no, it isn't. It isn't the wrong IP. You categorically gave me this IP. So I put the new IP in. But what happened was I had this high IP and now this lower IP. And there were some dramatic differences. Even though the laser field stayed the same, we were still looking at helium in its excited states. This shift in ionization potential really changed things. And I'm going to show you. So one more little bit of a little tool when I talk about my results is we're going to talk about the polarization axis, and that's in the Z direction. So when I talk about the configuration of the excited helium, the Z state is the one that's parallel to the polarization axis, and the one that's perpendicular is the X state. Okay, I hope that's okay. I know that you chemists call it different things, and this is hopefully we can come to an agreement. But yes, this is so when I refer to X, that's perpendicular to the polarization axis, and Z is parallel. So these are my results. On the top row, we have the low IP, and on the bottom row, we have the high IP. The diagrams to the left are the X orientation, so the perpendicular orientation, and the diagrams to the right are the parallel orientation to the polarization. These are, like I said, photoelectron momentum diagrams, and so it's measured by the momentum components. So what we would say is the perpendicular and the parallel momentum component, not to be confused with the orientation of the atom. Lots of parallel and perpendicular flowing around here, so hopefully you guys can stay with me. Here, I've done a dotted yellow ring, and that shows the 2 UP cutoff. Remember, that's where direct lives, and the rest, that big 10 UP arc, is the rescattered. So now I've highlighted 3 really interesting features. We have the yellow arrow, which shows that between the low and the high IPs, there's a different color. Why is that? Why is there a different color? Even though they're the same scale, why is there this thing that we call suppression? What's going on that we've just changed the IP and there's a dramatic difference between the rescattering ridge, almost non-existent in the case of the X orientation when we do the higher IP. The other interesting features is the green ring. Can you see in between the ring, there's all sorts of swirls and patterns and fringes and arcs. That is the interference patterns. And then with the red arrows, we can see this kind of like spilling outside of the ring. And that's a really key feature we're going to come to. And that's about orbit 3 behaving in this hybrid manner. The PMDs you have in front of you are all orbits. So that's orbit 1, orbit 2, orbit 3, orbit 4, all together, all interacting in their couples or triplets and on their own. So this is looking at the entire picture. We're not separating the orbits at all. Now, we are going to separate the orbits in this case. We're going to look first at the red arrow feature, the spilling. I've taken just orbit 3 here. After dissecting my diagrams and pulling out orbit 1 on its own, orbit 2, orbit 3, orbit 4, I could see that orbit 3 was the culprit that causes the spilling in the all orbit diagram that we saw previous. As you can see, it's living outside the 2 UP cutoff, but nor is it living in the 10 UP range. So therefore, it's not direct because it's outside, but it's not rescattered because it's not in that full arc. It's somewhere in between. It's a hybrid. So that was really interesting to find. Now, we're going to look at the interference patterns. So can you see those beautiful swirly fringes? If you look at these ones, they're slightly different to the ones that I showed you on the previous, because all I've done here is dissected orbit 2 and orbit 3 together. These create these beautiful spider-like fringes. So that's where my fella comes in. So if you look closely, you can kind of see like the legs of the spider coming out of the center, kind of like he's arching, kind of like the spider I've shown here. And this interference pattern is not shown in the SFA because 1, it treats the orbits as binary, either direct or rescattered. 2, it misses some of the quantum information that is available with the use of the Coulomb potential. Now, let's talk about this suppression. So there is between the low and the high IPs, there's a distinctive color change. as you can see indicated by the yellow arrows. So why just by varying IP does this happen? And as you can see, it's only in the direct region, the rescattered region, which is orbit 4, because orbit 4 is exclusively rescattered. So what is this suppression? And also, hey, what is that IP that I've been discussing? What are the actual numbers? Wow, the low IP is 0.15 AU, and the high IP is 0.175 AU. Not that much different, actually. Like, they're in the same magnitude. Like, why is it behaving so erratically or so differently just with this small change? So I think it's time that we actually look at orbit 4 and look at how it travels. So we look at the trajectory of orbit 4 and we can see where it pops out. Here is orbit 4, and here is a very extensive list of IPs. Now, on the diagram on the left, we've got the list, and it looks like all the lines are pretty much the same. But if we just move closely and just look at the two IPs in question that we have, the high and low, we can see that the low, the orange color, 0.15, gets pulled way down and then crosses over back to itself. And then here, it doesn't cross over. There is no crossover. So what's the difference? Why is there a crossing over for the low IP, and why is there crossing over for the high IP? How we can explain this is by looking at the green circle. Here is the point where it exits. This is the tunnel exit. This is where it leaves. It's where it's done its tunneling, and it's now going to be distorted. So let's zoom in. So here we go. This is the tunnel exit. So for the low IP, we have 5.48 AU. So we're looking at distances. We're looking at the parallel and perpendicular distances. And then for the high IP, we have 5.87. Some people would say, like, yeah, they're basically the same number. But actually what lies in between that number is a very incredibly important thing. So the tunnel exit of the high and low IP is affected by the Coulomb potential range. The Coulomb potential range sits in between them. So for the low IP, that is being dragged by the Coulomb potential. It's in the net of the Coulomb, like the Coulomb potential saying, ha, you're in my zone and I'm going to pull you. And that's why you get that strange crossover, because it's being more affected by the Coulomb potential. Whereas for the higher IP, it lives in a regime where actually it's outside of the force, the actual bubble of the Coulomb potential. And actually the laser field is more dominant. So therefore, it's completely acting in a laser field where you get the normal trajectory swoop rather than this crossover, this fight against the Coulomb potential. So the reason that the arrows are different on this kind of cartoon I've made is just showing who's winning the tug of war in these certain regimes. So how does this explain the suppression? The different IPs equal different tunnel exits. They're either in or out of the Coulomb range. Thus, the suppression seen occurs between the interplay of the Coulomb potential and the laser field. So why is this significant? The Coulomb potential has more influences than first thought, thus demonstrates another limitation of the SFA. Because remember, the SFA doesn't even include the Coulomb potential. So how can it be a well-defined model to explain the photoelectron holography from a theoretical standpoint if it doesn't include something that obviously, clearly has more of an impact than first thought of? So in summary, from those strange PMDs and the strange features I showed you, we've kind of assessed that rescattering is not limited to the polarization axis, because you see that spilling. The models produce quantum interference patterns with the ability to probe core dynamics and match with specific orbits. So we've seen those structures, those pretty images, and we've seen that we've been able to take them apart and see which orbit or orbit pairs or even orbit triplets give us the specific structures. Also, the direct and rescattering is not binary like the SFA, because we've seen that orbit 3 has a huge part to play with the quantum structures we see and also the spilling. We are also able to observe the signal of the perpendicular orientation to the field. So you know that X that we've been talking about, that X orientation, if we were doing the SFA, we wouldn't have been able to even produce plots like this. We wouldn't have been able to show them. So with the inclusion of the Coulomb potential and the other additional things that the CQSFA takes into account, we're able to show this because we're doing a non-Born type method. I mean, why look at a method that only shows you half the story, half the orientation of an excited helium or an excited whatever? So the inclusion of the Coulomb potential has a strong influence in the field dynamics, as shown by the suppression in the momentum distributions. So, like I said, the suppressions from the previous slide. So that's just one of my projects, you know. I do all sorts of things. I've been looking at other excited states, D states of model atoms, just to, you know, so I can play around with dynamics like the, you know, the ionization potential. Recently, I did a mini project investigating intensity. And so that's, rather than playing with the atom itself, we're actually playing with the laser field and seeing what happens there. And there's been some really interesting surprises. Also, I've been looking at symmetries and nodes of these more exciting orbitals and looking at how states compare, like varying the IP, but of a D state compared to a P state. Will the suppression be the same? Will it be the same type of suppression, or will there be something different? So all of this is wonderful because the CQSFA allows me to, like, basically change variables to investigate the strengths and weaknesses of the model. And essentially the strengths that we can exploit, but the weaknesses also show where we can work towards to fixing them or improving our model. So like I've kind of briefly mentioned, it's kind of been briefly said, I also do gin and tonic research, which I honestly think it's about time we start doing that. So maybe we can all have a drink and have a chat. So thank you so much for listening to my rambling. I apologise with the bit of technical issues that we've had through this, but I hope you all enjoyed. So there we go.
It's so annoying when there's some clap emojis, but as you said, it's really hard to like gauge people's reaction. But I thought it was a really brilliant talk, super interesting. So I think we'll open the floor to questions. If anyone has a question, if you just want to raise your hand, or if you want to type it in the chat, and I think Abbie, you'll be able to see the questions, or I can read them out if not. I can't see on the thing if anybody's got a question.
But you could literally, anyone can ask me anything, either about my, whatever, like ask me anything. Like, you're welcome to ask me about my work. You're welcome to ask me about my diversity inclusion stuff. I honestly don't mind. Like, as a PhD student, I wear many hats. So it's all part of the experience. And so, yeah.
I am.
Also,
sorry, someone.
Ask me about PhD life or applying for PhD, what it's like. That could also be something you could ask me about. But, okay.
There is a question. Is there a magnetic energy involved? That's from
No. So we look at the laser. So it's the laser field is just photons. So there's no magnetic. I see. I've got one of my colleagues is on this chat, so I'm like, oh, like, am I saying it wrong? So no, there's no magnetic field involved.
Abbie, I was really interested in your imposter syndrome chat. It's something I did a seminar in, and it's something that I really want to bring into chemistry and into the department. I think it's a really, really big deal. It's a really big deal for women. It's a really big deal if you're BIM. It's a really big deal if you're working class. So that's really cool that you brought that up. Thank you.
That's all right. Like, it's in the weirdest thing that's ever happened to me with imposter syndrome. So after that talk at the RI, loads of people like clapped and everything, but this little wizened old man came like running down the stairs at me, and he was like, "I'm 90 years old," and I was like, "Cool, like, nice." And he was like, "I suffer from imposter syndrome." He was like, I never knew that that's what it was called. And he was like, "I've done all this research over the years, but I still doubt myself." So I looked at him and I was like, "Thank you for sharing your story. Literally, it doesn't stop, guys. Like, you can be a 90-year-old white man who is at the top of his field, and he still suffers from it. So if you have any doubts or anything, like, honest to God, feel them, appreciate them, because they are part of your history, they are part of your story, but also don't give in to them, because the reason that you're here is because you're doing a really good job. Like, I said to Carla, like, oh, you just picked me because I'm a diversity hire. And she's like, no, she's like, I need work doing. Do you think I was going to hire somebody who couldn't do the work just because they tick the box? So obviously feel all your emotions, but sometimes that little voice in your head that tells you you're not good enough or you're not here for that right reason, it's lying to you. It's not true. You're here because you're doing good.
I think that's a really kind of important message. I love that story about the old guy. That's brilliant. Yeah. Oh, I'm the colleague. Someone's answered the question. I think it's very prevalent in academia as well, because you kind of live in this bubble of, you know, for example, you'll experience it when you get your PhD, Abbie, is people are very impressed outside of academia when you're a doctor. They can't believe it. It's like, wow.
Yeah.
And yet in academia, it's like, so what? Like, yeah. Wait till you're a professor before you start getting pleased about it.
Exactly.
And when I was on the seminar, she said that one of the stupidest things she heard from academia was someone was like, well, I just feel so rubbish because I only speak 5 languages, and they were like a language tutor or something. And I think it's definitely something very prevalent. So I think the more we talk about it, the better.
Yeah, because everyone has this habit of comparing themselves to others, but like, you can't compare tomatoes and potatoes. Like, we're all really different and we all come from different things, and just the fact that like we're here, it's just, yeah, it's like, just imagine if I speak kind of 2 languages, and if someone was like, oh yeah, like, it's not impressive speaking 5, from somebody who's not a language tutor, I'd be like, shut up, that's crazy. But obviously in their field, they're working with colleagues who may be speaking 7, 8, 9, who knows?
Yeah.
Like, it's insane.
That's really reassuring to hear, especially as an undergrad, that everyone feels it.
Yeah, I mean, you feel it in undergrad, you feel it forever. You're even outside of academia, outside of work, there'll be times where you might feel imposter in your friendship group, or if you're, I don't know, if you're a parent, or, I mean, obviously I haven't experienced that yet, but like, are you doing the right thing? And it will constantly stay with you, and it's just important to know that there's a name for it. It's not just you going crazy. Like,
yeah, definitely. I have a question about, sorry, Christopher, you go.
Oh, okay, you can go first.
Okay. After you've published your work, where do you see the future of the field?
Not in my hands. I leave academia, to be honest. But with imaging things like this, if you can image an atom really well and look at the dynamics and look at the behaviors, you could look at molecules. And obviously molecules are important because they make up everyday life. And looking at what they do, you can target them specifically to look at that certain thing that you've found that they do. So in a way, it's imaging means that you can see the picture, or you can look for specific behaviors. So if you apply that to like the medical world, you could use a type of imaging to maybe look at when a molecule is being a bit naughty, that it's like mutating or so on, or it's behaving in a different way. You can look at the imaging of being able to change some sort of solid or some sort of molecule in order to do like, so for instance, there's a project that some friends of mine work in ISIS in Oxford, and they looked at cheese, and because cheese is so good of protein and calcium, they're looking at a way that they can change actually the structure so it actually lasts longer. So then you could send it to places that are malnourished, in order to give those people more protein and calcium. So it's anything with imaging enables us to tell a story, but also look at certain parts of it. I hope that makes sense. I mean, I'm here in the food chain doing some theory, and electron holography can go so far. I know that I went to a seminar where they were looking at liver and the way that blood moves in the liver through holography, and I was like, whoa, I'm part of the medical world now. I mean, I'm not, but like, it was just so impressive to see something I do a very small part of could be used for something else.
That's so interesting.
Yeah, but
so
also
could I have a I have a question about, because the thing that you have done, like, correct me if I'm wrong, I'm just second year undergrad, so apologies in advance for stupid question, but you're basically, what you're doing, you're correcting a certain approximation and you're creating another model. So do you know if your model has certain like flaws, and does it like collapse with any like, you know, data? And
my model is perfect and there's nothing wrong with it and it's wonderful. No, my model experiences some issues with branch cuts and singularities at certain points. The stability factor has resolved some of them. Also, when you look at stuff that's out of the barrier of the potential well, like over the barrier stuff begins to break down. But it's like the SFA is still a really useful model if you wanted to do this job. But then when you wanted to do another job, it doesn't work. It's like every model, there might be some grand unified theory that explains everything, but like depending on the model, it kind of gives you a peek at the certain thing that you want. I mean, the reason why ours is impressive, I say impressive because obviously I'm part of it, so I can't really like say it's amazing. Like, of course, to me it's my life, is that involves, like I said, the Coulomb potential. And you guys must have come across the Coulomb potential even in school. You know, it's that like Q over R squared.
Yes.
So
secondary school, I think. Could I, like, next question, like actually following this question, like, are you planning to actually like furtherly you know, like improve your model by including like certain interactions of electrons, or is this model like good enough for like your research and you're not planning to improve it? And what kind of interactions could we like take into account?
When I started, my model couldn't do excited states. Now they can, because I made it do excited states. I began to look at the geometry and simulated the excited states and the effective potential and so on and so forth. So that was one improvement. But what I am looking at is that there's an atom that comes in a pair. Oh my God, I'm with chemists now, so I actually have to remember what it's called. It's something. They do it with my collaborators in Canada. And the thing is, because you could have one excited state where it's, let's say, X, but the other one could be Z. So obviously I could look at X and look at Z, but I need to look at them together because they're a pair. So I'm in my head figuring out how I can change my model to include two atoms at once, and then also in itself different states, and see what the interference patterns would come, because obviously isolating helium in an excited state is really hard to do an experiment. But then obviously there's more common excited states, more robust, able to do it. But obviously they become more complicated, and therefore my model needs to meet that point. So yeah, that's kind of it. Like, that's something that I would like to do. But at the moment I'm kind of stuck on some projects I'm really enjoying, and that's kind of like maybe something that I'll begin before I leave my PhD. Who knows? But
okay, thank you for your answer. It was a brilliant talk, I think.
Also molecules as well. But like I said, they are complicated because there's like so much going on and stuff, and there's bits everywhere. Like, so yeah.
Thank you for your talk.
All
right. It was brilliant, I think.
Yeah, thanks again, Abbie, so much.